Everything you believe about reality is wrong, not slightly off, not in need of a small correction. Fundamentally, structurally, irreversibly wrong. The chair beneath you, the light around you, the thoughts forming in your mind right now, none of it works the way you think it does. And the scientists who proved this, they spent the rest of their lives wishing they hadn't, not somewhere distant, not in some exotic laboratory hidden beneath a Swiss mountain, or aboard a satellite spinning silently through the void of space. Right here, right now, in this very moment, particles that make up the atoms in your body, the electrons orbiting the nuclei of every cell in your brain, in your hands, in your eyes as they read these words, are doing something that should not be possible. They exist in multiple places at once. They are, in the most literal scientific sense, in two states simultaneously, spinning left and right at the same time, existing and not existing in the same breath. Right up until the moment something observes them, and in that instant of observation, the entire structure of possibility collapses. Like a dream dissolving the moment you open your eyes. Like a story that changes based on who is reading it. This is not a metaphor. This is not a convenient simplification for popular audiences. This is the most tested, most precisely verified, most rigorously confirmed theory in the history of all human science. And it says, in language as cold and mathematical as anything ever written, that the universe does not have a definite, singular reality until something looks at it. Let that settle for just a moment. The universe you think you live in, the solid, predictable, cause and effect universe where a rock thrown upward must come down, where a coin is either heads or tails, where a cat is either alive or dead. That universe may not be the fundamental nature of reality at all. It may be a kind of emergent illusion, a story the universe tells about itself when it happens to be observed. Beneath it, at the deepest level science has ever probed, reality is something far stranger, far more beautiful, and far more terrifying than anything human intuition was ever designed to comprehend. The theory is called quantum mechanics, and it has been with us for over a century. In that century, it has given us transistors and lasers, MRI machines and solar panels, the entire digital world you inhabit. It has predicted the behavior of subatomic particles with an accuracy that staggers the imagination, correct to more than 10 decimal places, a level of precision equivalent to measuring the distance from New York to Los Angeles to within the width of a single human hair. And yet, not a single physicist alive today fully understands what it means. Not one. Richard Feynman, arguably the greatest physicist of the 20th century, said it plainly and without embarrassment. I think I can safely say that nobody understands quantum mechanics. He wasn't being modest. He wasn't being poetic. He was stating, as a matter of bare scientific fact, that the theory which underpins all of modern technology, which describes reality at its most fundamental level with breathtaking precision, that theory contains at its core a mystery so deep, so unsettling, so philosophically explosive, that it has divided the greatest minds in science for over 100 years. Some believe quantum mechanics tells us that reality branches endlessly, that every possible outcome of every possible event spawns an entirely new universe, so that the cosmos is not one thing, but an infinite, ever-multiplying tree of parallel worlds, each one as real as this one, each one occupied by a version of you who made a different choice, who lived a different life. Some believe it tells us that the universe is fundamentally made not of matter, not of energy, but of information, that at the deepest level, reality is a computation, a kind of cosmic code, and that the physical world is nothing but the output of that code. Some believe it tells us that there is no objective reality at all, that every observer creates their own private reality, that the universe is not something that exists independently of the minds that perceive it, but something that is, in some profound and unsettling sense, made of observation itself. And some believe that quantum mechanics, for all its spectacular success, is incomplete, that beneath it lies an even deeper theory, one that will finally reconcile the quantum world with the world of gravity and curved spacetime that Einstein gave us, a theory so profound that it will not merely extend our understanding of physics but shatter and rebuild it entirely. This documentary is about all of that. It is about the century-long crisis at the heart of physics, about the experiments that revealed impossible things, about the arguments between titans of science that became, in their way, the greatest intellectual drama in human history, about what quantum mechanics might really mean for reality, for consciousness, for the nature of time itself. But it begins, as all great mysteries do, with a question nobody thought to ask, and with a man standing in front of a furnace watching iron glow red in the dark, wondering why. The year is 1900. The place is Berlin, and the man's name is Max Planck. He is not, at this moment, trying to change the world. He is not pursuing a grand theory of the cosmos. He is, in the most practical and unglamorous sense, trying to solve an engineering problem. A very boring engineering problem, as it happens, about the color of light emitted by hot objects. Here is what you need to know. When you heat metal, when you heat anything, really, it glows. Heat it a little, it glows dull red. Heat it more, it turns orange, then yellow, then white, then blue-white. The color of the glow changes with temperature, and in the late 19th century, physicists wanted to understand exactly why. Not for poetic reasons, for industrial ones. Factories needed to know how hot their furnaces were, and color was the easiest way to tell. The problem was simple to state and maddening to solve, using the physics of the day, what we now call classical physics, the beautiful framework that Newton and Maxwell and their colleagues had built over 2 centuries. You could try to calculate the exact spectrum of light emitted by a perfectly absorbing object at a given temperature. And when you did that calculation, you got an answer that was not merely wrong, it was catastrophically, absurdly impossible wrong. The classical calculation predicted that any warm object should emit infinite energy at high frequencies, an infinite amount of energy, from a pot on the stove, from your own body. Physicists call this the ultraviolet catastrophe, and it was not a problem to be worked around or refined. It was a fundamental breakdown. The most successful framework in the history of science was producing infinite nonsense when applied to one of the most basic phenomena in nature. Max Planck stared at this problem for years. He tried every mathematical trick available. He twisted and bent the classical equations. Nothing worked. And then, in a moment that he would later describe as an act of desperation, he tried something he himself found almost physically repugnant. He assumed that energy was not continuous. In classical physics, in all of physics up to that point, energy was assumed to be like water. You could have any amount of it, a tiny amount, a large amount, any fraction in between. It flowed smoothly, continuously, without gaps. This was not a controversial assumption. It was barely an assumption at all. It was simply how the world obviously worked. Planck proposed, almost as a mathematical trick with no physical meaning attached, that energy came in discrete packets, lumps, chunks, that you could not have just any amount of energy but only specific, quantized amounts, multiples of a fundamental unit that he called simply a quantum. The size of this quantum was determined by a new constant of nature, which we now call Planck's constant, written as the letter h, and it is almost unimaginably small, a number so tiny it makes the diameter of a proton look like the distance to the moon. When Planck ran the numbers with this absurd assumption built in, something remarkable happened. The catastrophe disappeared. The calculation agreed with experiment perfectly, beautifully, without a shred of leftover error. Planck himself was deeply uncomfortable with what he had done. He suspected it was a mathematical trick, a useful fiction. He spent the next decade trying to derive his formula from classical physics, trying to show that the quantization was not real, not fundamental, just a convenient sleight of hand. He never succeeded, because it was not a trick. He had cracked open the universe, and something strange was looking back. 5 years after Planck's discovery, a young patent clerk in Bern, Switzerland, you already know his name, took Planck's idea and did something both obvious and radical. He took it seriously. He applied it not just to the abstract mathematical problem of thermal radiation, but to a real physical phenomenon that had been puzzling scientists for years: the photoelectric effect. When you shine light on certain metals, electrons are not loose from the surface. This is the photoelectric effect, and it is the basis of solar panels and photodetectors. But classical physics had a problem with it. According to classical physics, light was a wave, and a brighter wave should carry more energy and knock out more energetic electrons. But experiments showed something different. The energy of the knocks out electrons depended not on the brightness of the light, but on its color. its frequency. Red light, no matter how bright, couldn't knock out electrons above a certain energy. Blue light, even very dim, could. Albert Einstein looked at this and saw Planck's quantum, not as a mathematical trick, but as a physical reality. Light, he proposed, was not just a wave. It came in discrete packets, particles of light that we now call photons. Each photon carried an energy proportional to its frequency. High-frequency blue light carried high-energy photons. Low-frequency red light carried low-energy photons. And you either had enough energy to knock out an electron or you didn't. Brightness just meant more photons, not more energetic ones. This was, on the surface, a neat solution to a puzzling experiment. What it actually was, though no one fully grasped this at the time, was the first crack in the dam. Because if light, which every experiment for 200 years had confirmed was a wave, a continuous undulation of electric and magnetic fields spreading through space, if light was also a particle, then something was deeply, fundamentally wrong with how humans understood the nature of physical reality, and it was going to get much worse. Over the next 2 decades, as physicists dug deeper into the quantum world, the strangeness escalated with every experiment. It was as if reality itself was pushing back, as if the universe was trying to tell them something that human language and human intuition simply weren't built to receive. In 1913, a young Danish physicist named Niels Bohr proposed the model of the atom in which electrons orbited the nucleus like tiny planets, but only in specific, allowed orbits. They could not be between orbits. They could jump from one to another, not by traveling through the space in between, but by simply vanishing from one place and appearing in another, instantaneously, without passing through the intervening space at all. Physicists call this a quantum jump, and even then, even as the phrase was coined, there was something about it that felt like a violation, not just of existing physics, but of some deeper principle about how existence itself was supposed to work. Then came Louis de Broglie, in his 1924 doctoral thesis, a thesis that his professors almost didn't accept, thinking it too speculative. De Broglie proposed something that seemed almost deranged. If Einstein had shown that light, a wave, could behave like a particle, perhaps particles, electrons, atoms, actual physical objects, could behave like waves. Perhaps everything had a dual nature. Perhaps the distinction between waves and particles, one of the most fundamental distinctions in all of classical physics, was not a distinction at all. His committee passed his thesis. They sent it to Einstein for review. Einstein wrote back that de Broglie had lifted a corner of the Great Veil. 3 years later, experimenters shone a beam of electrons at a crystal and watched the electrons diffract, spread out, interfere with each other, produce the classic pattern of waves. Electrons were waves. Matter was waves. The most solid things in the universe were ripples in something that didn't even have a name yet. And then, in 1926, a physicist named Erwin Schrödinger sat down and wrote an equation. The Schrödinger equation is one of the most beautiful and most disturbing things in science. It describes how quantum systems evolve over time. It is deterministic. Given the state of a quantum system now, it tells you with perfect precision what the state will be at any future time. In that sense, it is as orderly and lawful as Newton's equations of motion. The universe, according to Schrödinger's equation, is a precisely clockwork place, except for one thing, one small, catastrophic, civilization-shaking thing. The thing that the Schrödinger equation evolves over time is not a particle. It is not a wave in any physical medium. It is something called a wave function, a mathematical object that encodes not the actual position or momentum of a particle. The probabilities of finding the particle in various positions or with various momenta, if you were to measure it, the particle does not have a definite position. It is, in the mathematical language of the theory, spread out, smeared across space. Present everywhere, its wave function has amplitude, with a probability of being found at each location proportional to the square of that amplitude, until the moment of measurement. In the moment of measurement, when a detector clicks, when an instrument registers a result, when the quantum system interacts with the classical world, the wave function collapses. The smeared-out probability distribution instantaneously becomes a single definite outcome. The electron that was everywhere at once is suddenly here, at this specific point, and nowhere else. This collapse of the wave function is the heart of the quantum mystery. It is the thing that every interpretation of quantum mechanics, every philosophical position, every alternative theory, every argument between the greatest physicists of the century is ultimately about, because nobody, in over 100 years, has been able to explain what it means. Let us be precise about what the mystery actually is, because it is easy to nod along to phrases like wave-particle duality and superposition and feel as though you understand something, when in fact you are simply reciting words that gesture at a problem without touching it. Here is the problem. The Schrödinger equation never stops. It evolves quantum systems forward in time, always, without exception, smoothly and continuously. According to this equation, superpositions, particles in multiple states at once, do not just persist, they spread. They infect other particles. They grow. If a particle in superposition interacts with the detector itself becomes part of the superposition. If a scientist reads the detector, the scientist becomes part of the superposition. The entire universe, according to the Schrödinger equation, should be one vast, growing, entangled superposition of all possible states of all possible things. But we don't experience that. We experience a single, definite world. When we look at an electron, we see it here, not there. When we flip a coin, we see heads or tails, not some smeared-out mixture of both. When we read a measurement, we get a number. One number, not a probability distribution. The world we live in is, at the level of everyday experience, utterly definite and singular. So where does the quantum weirdness go? What happens to the superposition? What collapses the wave function, and how and why? These questions have a name. Physicists call it the measurement problem, and despite a century of effort by some of the finest minds in human history, it has not been solved. To understand why it is so difficult, you need to understand what the standard textbook answer actually says, and why that answer is philosophically catastrophic. The standard answer, the one drilled into physics students for a century, is something called the Copenhagen interpretation, formulated primarily by Niels Bohr and Werner Heisenberg in the late 1920s. And the Copenhagen interpretation, at its core, says something remarkable. Stop asking. Not in those words, of course, but its essential message is that quantum mechanics is a tool for predicting the outcomes of measurements. And the question of what is happening between measurements, the question of what the wave function really is, of what collapse really means, of what exists when we're not looking, is not a physics question. It is metaphysics, it is philosophy, it is outside the proper domain of science, and physicists should not worry about it. Shut up and calculate. For decades, this worked. As a practical program, the Copenhagen interpretation was extraordinarily successful. You could use quantum mechanics without worrying about what it meant, and the calculations came out right every single time. The transistor in your phone doesn't care whether wave function collapse is real. The laser that reads your music doesn't need a coherent ontology. So generations of physicists learned to compartmentalize, to use the theory without thinking too hard about what it was saying. But some of them couldn't stop thinking about it, and what they found when they thought hard enough was not reassurance. It was something much darker. Here is one version of the darkness. It is called the problem of Schrödinger's cat, and it was invented by the very man who wrote the equation. In 1935, Erwin Schrödinger was deeply troubled by the implications of quantum mechanics, and he devised a thought experiment to illustrate why. Imagine, he said, a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a vial of poison, and a hammer rigged to smash the vial if the Geiger counter detects radioactive decay. The radioactive atom has a 50% chance of decaying in 1 hour. Now here is the quantum part. The radioactive atom is a quantum system. Before measurement, before any detector or observer becomes aware of whether it has decayed, the atom exists in a superposition, both decayed and not decayed at once. According to the Schrödinger equation, this superposition spreads to the Geiger counter, to the hammer, to the vial, to the poison, and to the cat. After 1 hour, with the box still sealed, the quantum state of the entire system is a superposition of cat alive and cat dead. Is the cat alive or dead? In the Copenhagen interpretation, the question doesn't have an answer until you open the box and look. Until observation occurs, the cat is neither alive nor dead, but in a superposition of both states. This is not a comfortable answer. It is not even a coherent one, because the Copenhagen interpretation never tells you what counts as an observation, what counts as a measurement, what distinguishes the quantum system from the measuring apparatus. Is the Geiger counter an observer? Is the cat? If a cat can't be in superposition because it's big enough to count as classical, where exactly does quantum become classical? At what scale? At what number of atoms? Nobody has ever answered these questions. Nobody, in over 80 years since Schrödinger wrote them down, has answered them. And if that bothers you, if you find it unsatisfying that the most powerful theory in science is built on a foundation that cannot define its own key terms, then you are in excellent company. But that was only the beginning. Kaz, there is a second layer to the mystery, one even stranger than superposition, one that Einstein himself said made him feel as though something had gone deeply wrong at the heart of physics. Something that he called, with a phrase that has echoed through the decades, spooky action at a distance. It is called quantum entanglement, and it may be the most extraordinary phenomenon in all of nature. Here is what happens. If two particles interact in certain ways, they become entangled. Their quantum states are correlated in a way that cannot be explained by any classical, local, separable physics. You can then separate these particles by any distance you like, across the room, across the city, across the galaxy, and when you measure one of them, something strange happens to the other. Instantly. Instantaneously. Faster than light. Measure the spin of one entangled particle and find it spinning up, and the other particle, no matter how far away, will be found spinning down, every time, without fail, with a statistical precision that cannot possibly be explained by the particles simply having predetermined values, as Einstein believed. John Bell proved this mathematically in 1964 in one of the most important theorems in the history of physics, and in 1982, Alain Aspect and his colleagues in Paris confirmed it experimentally. The correlations between entangled particles are too strong by a mathematically precise, inescapable amount to be explained by any theory in which the particles carry hidden instructions decided at the moment of their creation. The universe is not locally realistic. It does not obey the intuition that distant objects can only influence each other through signals that travel through space at finite speed. Something connects these particles across space in a way that has no classical explanation, no mechanism, no signal we can detect, no carrier, just correlation, instant and perfect and mysterious. Einstein died convinced this was wrong. He was wrong. The universe, it turns out, is doing something that by every right it should not be able to do. And nobody understands how, before we go further into the depths of the mystery, we need to ground ourselves. We need to understand, as clearly as possible, what quantum mechanics actually says, not in the vague, approximate terms of popular science, but in the precise language of the theory itself. Because the strangeness is not a consequence of imprecision. The strangeness becomes more acute the more precisely you understand the theory. Think of quantum mechanics as built on a small number of extraordinarily powerful ideas. Ideas that are individually simple to state and collectively world-shattering to accept. The first idea is superposition. Any quantum system, a particle, an atom, a molecule, can exist in a superposition of multiple states simultaneously, not one state or the other, randomly chosen, not one state with some uncertainty about which one, both, simultaneously, superimposed on each other, like two songs playing at once. The wave function of a particle in superposition is literally a sum of multiple different states, each with its own amplitude and phase, all present at the same time. The second idea is that the wave function is everything. It contains all the information that can possibly be known about a quantum system. There is no hidden layer beneath it where the particle secretly has a definite position and momentum that we just haven't measured yet. The wave function is not our ignorance about a definite reality. It is the definite reality. The particle doesn't have a position until it's measured. This is not a statement about our knowledge. It is a statement about what is. This idea, that the wave function is the complete description of reality at the quantum level, is called the completeness assumption, and it was one of the central bones of contention between Bohr and Einstein. Einstein believed it was wrong. He believed quantum mechanics was incomplete, that the wave function described a statistical ensemble of particles, each of which secretly had definite properties, and that one day a deeper theory would reveal those hidden properties and restore the determinism and locality that classical physics had always assumed. Bohr disagreed. After decades of arguments and multiple failed attempts by Einstein to find a loophole, experiment has vindicated Bohr. The wave function is the complete description. There is nothing underneath it. The third idea is Heisenberg's uncertainty principle. This is probably the most famous idea in quantum physics and the most frequently misunderstood. The uncertainty principle does not say that we cannot measure position and momentum simultaneously because our instruments are too crude or because the act of measurement disturbs the particle. It says something far more radical. A particle does not simultaneously have a definite position and a definite momentum. These properties do not both exist at the same time. The more definite the position, the more spread out the momentum, not because of technological limitation, but because the universe itself does not permit both to be simultaneously real. This is not a statement about measurement, it is a statement about existence. Position and momentum are, in the language of quantum mechanics, complementary observables, and a particle cannot have definite values of both at the same time, any more than a word can simultaneously be a noun and a verb without context. The fourth idea is the Born rule, the rule that connects the abstract mathematical wave function to the concrete observable world. When you measure a quantum system, the probability of getting a particular result is equal to the square of the wave function's amplitude at that result. This rule works perfectly. It has never once failed in a century of testing. It predicts the statistics of quantum measurements with precision that beggars belief. And it is completely mysterious, because nobody knows why the universe should obey it. It is not derived from anything deeper. It is simply stated as a postulate of the theory, a rule the universe follows with no further justification. The fifth idea is entanglement. When two or more particles interact, their wave functions can become correlated in a way that cannot be factored apart. You cannot describe each particle independently, because the quantum state of each particle depends on the state of the other. They are not two separate systems any longer, but one joint system, described by a single wave function that spans the space between them. This connection persists no matter how far the particles are separated. It cannot be explained by any mechanism that respects locality. The principle that what happens here cannot instantaneously influence what happens there. Together, these five ideas form the core of quantum mechanics. And from these five ideas that are precise, mathematical, and empirically verified to extraordinary precision, the mystery flows. Because together they imply things about the nature of reality that are not merely counterintuitive, but, depending on which interpretation you accept, either deeply strange or frankly impossible. And the deepest, most important, most contested of these implications is the one we keep circling back to, the measurement problem. What happens when a quantum system is measured? What is measurement really? And what happens to all the other possibilities, the other branches of the wave function, when one outcome is selected? That is the question. And now let us look at what happens when you take it seriously. If you're enjoying this exploration of one of science's deepest mysteries, consider subscribing. There is much more to come, and what we're about to reveal will make everything you've heard so far seem like the prologue. Not a thought experiment this time. Not a Gedanken exercise scribbled on a blackboard. A real experiment done in a real laboratory with real equipment that produced results so strange that even physicists who knew quantum mechanics were stunned. An experiment so carefully designed, so precisely executed, and so utterly inexplicable by any classical means that it has been called, without exaggeration, the most beautiful experiment in physics. It is called the double-slit experiment. The setup is almost embarrassingly simple. You have a light source, or an electron gun, or indeed a source of any quantum particles at all. In front of it, you place a barrier with two narrow slits cut into it. On the far side of the barrier is a detector screen that records where particles land. That's it. That's the whole apparatus. What happens when you fire particles at this barrier? If the particles were classical objects, like tiny bullets, definite and solid, passing through one slit or the other, they would make two bands on the detector screen, one behind each slit. That's what bullets do. That's what classical physics predicts. But that's not what happens. What happens instead is that the particles create an interference pattern on the detector screen, the characteristic alternating bands of high and low intensity that you get when two waves overlap and interfere with each other. The particles are behaving like waves. Each particle somehow impossibly passes through both slits at once, interferes with itself, and lands in a pattern determined by wave interference. Astonishing. But it gets stranger. What if you fire the particles one at a time? Surely then, with no other particle to interfere with, each individual particle must go through one slit or the other, and the interference pattern should go away? It doesn't go away. Even when particles are fired one by one, so slowly that there is never more than one particle in the apparatus at a time, the interference pattern builds up gradually, dot by dot. Each individual particle, with no other particle to interfere with, somehow still produces the interference pattern. As if each particle interferes with itself, as if each particle somehow explores both at once, and the result of that exploration determines where it lands. The particle is in superposition. It travels through both slits simultaneously. The interference pattern is the signature of this superposition, but here is where it becomes truly terrifying. What if you set up a detector, just a small innocuous detector, at the slits to find out which slit each particle goes through? Surely you think this won't change where the particles land. Surely knowledge of the path doesn't affect the destination. But it does. The moment you place a detector that could, in principle, tell you which slit the particle went through, even if you never look at the detector, even if you never read the result, the interference pattern disappears. The particles start landing in two bands, like bullets, like classical objects. The mere possibility of knowing the path, the mere existence of information about which slit the particle chose, destroys the interference pattern. The superposition collapses, the quantum behavior vanishes. And if you then destroy the which path information, if you erase the record the detector created, so that the information about the particle's path no longer exists anywhere in the universe, the interference pattern comes back. The act of erasing information restores quantum behavior. This is not magic. This is a real experiment published in 2000 by Yoon-Ho Kim and colleagues called the Delayed Choice Quantum Eraser. The information about the particle's path was erased after the particle had already landed on the detector screen, and the pattern of landings retroactively correlated with the erasure. The past appears to depend on what happens in the future, not in a way that allows you to send information backward in time, but in a way that makes the very concept of a definite past deeply, deeply problematic. Read that again. Take your time with it. The past appears to depend on what happens in the future. This is not an isolated weirdness. It is a thread that, when pulled, unravels something enormous. In the 1970s and 80s, physicist John Archibald Wheeler, one of the most creative thinkers in 20th century physics, the man who coined the term black hole, devised a variation of the double-slit experiment that he called the delayed choice experiment. In Wheeler's version, the choice of whether to measure which path information or to observe the interference pattern is made after the particle has already passed through the slits. If the particle somehow decides at the slits whether to behave like a wave or a particle, it would need to know in advance what kind of measurement awaits it. But the decision is made after the particle has already passed through. There is no way the particle could have known. Wheeler concluded, and subsequent experiments have confirmed, that the particle does not decide at the slits. It has no definite state. It is neither wave nor particle until the measurement is made, and the measurement reaches backward in time, not in any mystical sense, but in the precise sense that the outcome of the measurement is correlated with what the particle was doing at the slits, retroactively, even though the particle had already passed through before the choice was made. Wheeler extended this thought to a cosmic scale. He proposed an experiment using quasars, objects billions of light years away, whose light has been traveling since the early universe. The light from a quasar is bent by a galaxy lying between the quasar and us, splitting into two paths that arrive at Earth separately. This is gravitational lensing, a real phenomenon. Wheeler's thought experiment asks, what happens if you use a beam splitter to choose, at the moment the quasar's light arrives, whether to observe which path it took, or to observe the interference between the two paths? According to quantum mechanics, your choice, made now, today, in the present, retroactively determines which state the quasar's light was in as it traveled through the universe, billions of years ago, before the Earth existed, before the Sun existed. Experiments along these lines have been done, though not at cosmic distances. In 2007, physicists at the Australian National University performed a delayed choice experiment using atoms, and in 2015, a group at the University of Vienna performed one using entangled photons separated by 143 kilometers. The results agreed with quantum mechanics every time. The present, in some sense, shapes the past. And that was only the beginning of what things would become. Let us go even deeper. Let us talk about something called quantum non-locality, because it is here that the mystery reaches its fullest, most disturbing expression. In 1935, Einstein, together with his colleagues Boris Podolsky and Nathan Rosen, published a paper that was intended as a reductio ad absurdum, a proof by contradiction that quantum mechanics must be incomplete. The argument, known as the EPR paradox, went like this. Consider two particles that are entangled. Their quantum states are correlated. Separate them by a great distance. Measure the position of particle A with absolute precision. According to quantum mechanics, this measurement instantaneously affects the state of particle B, even though B is far away. But this violates a principle that Einstein considered sacred, the principle of locality, which says that objects can only be directly influenced by their immediate surroundings, and that influences can travel no faster than light. Therefore, Einstein concluded, quantum mechanics must be incomplete. There must be hidden variables. Properties of the particles, determined at the moment of their creation, that predetermine the outcomes of all measurements. Quantum mechanics doesn't describe these hidden variables, so it describes the particles incompletely. But some future, deeper theory would describe them, and when it did, the apparent non-locality would turn out to be an illusion. For nearly 30 years, the EPR argument sat at the boundary between physics and philosophy, untestable and unresolved. Then, in 1964, a physicist at CERN named John Stuart Bell did something extraordinary. He proved a mathematical theorem, now called Bell's theorem, that showed the EPR debate was not philosophical at all. It was experimental. Bell showed that any theory with local hidden variables, any theory in which the particles have predetermined properties decided locally, without spooky action at a distance, would necessarily produce correlations between measurements on entangled particles that obey certain mathematical inequalities. Quantum mechanics predicts correlations that violate those inequalities. And the violation is not marginal. It is large, clear, and testable. Bell had found a way to make the dispute between Einstein and Bohr into an experiment. All you had to do was measure the correlations, and if they violated Bell's inequalities, Einstein was wrong, and nature was genuinely irreducibly non-local. In 1972, John Clauser and Stuart Friedman performed the first Bell test. The correlations violated the inequalities. In 1982, Alain Aspect and his colleagues in Paris performed a more rigorous test, with detectors switching their measurement settings randomly after the particles were in flight, so that neither particle could possibly send a signal to the other about what kind of measurement was coming. The correlations still violated the inequalities, and in 2015, 3 separate groups around the world, in Delft, in Vienna, and in the United States, performed loophole-free Bell tests, closing every possible classical escape route. The violations stood. The universe is non-local. This is not an interpretation. It is not a philosophical stance. It is an experimental fact, as solid as the existence of gravity. The universe contains correlations between distant, separated particles that cannot be explained by any theory in which each particle carries its own independent information about how to respond to measurements. Einstein was wrong. The universe does engage in something very much like spooky action at a distance. But this is crucial. This non-locality cannot be used to send information faster than light. You cannot use entanglement to communicate because the correlations are only visible when you compare the results from both detectors. And that comparison requires ordinary classical communication that travels no faster than light. The non-locality is real, but it is somehow frustratingly useless for violating causality. The universe seems to know the loophole. It can be non-local, as long as it's not the kind of non-local that will let you transmit information instantaneously. This raises the question that sits at the very edge of what we can currently understand. If the universe is non-local but in a way that carefully prevents faster-than-light communication, is that a coincidence? Is there a deeper principle at work? Some deeper law that allows non-locality but constrains its expression precisely at the point where it would become causally dangerous? Nobody knows. This is one of the open frontiers of fundamental physics. The history of quantum mechanics is, in part, a history of extraordinary minds wrestling with a theory that defied their intuitions. It is one of the most dramatic intellectual stories in human history, full of heated arguments, personal rivalries, midnight epiphanies, and catastrophic failures that turned out, in the end, to be more important than any of the successes. Let us spend some time with the people at the center of it. Niels Bohr is, in many ways, the most important figure in the quantum story. The founder of quantum theory as a coherent framework, the man who more than any other shaped how physicists thought about what quantum mechanics meant. Bohr was not merely a physicist, but a philosopher of physics. A man who thought deeply about the nature of knowledge and observation and the relationship between a theory and the reality it describes. Bohr's central insight, the one that defines the Copenhagen interpretation, was that quantum mechanics is a theory of what we can observe, not a theory of what is. The wave function is not a picture of physical reality, but a tool for computing the probabilities of measurement outcomes. The question, what is the electron really doing between measurements, is not a meaningful question because physics can only speak about what is measurable, and between measurements, nothing is measurable. The boundary between the quantum world and the classical measuring apparatus is not sharp, but it is real. In trying to dissolve it by applying quantum mechanics to the apparatus itself is a category error. Bohr was brilliant, and his position was intellectually defensible, but it was also deeply unsatisfying to anyone who believed that the purpose of physics was not just to make predictions, but to understand reality. And nobody was less satisfied with it than Albert Einstein. The Einstein-Bohr debates are legendary. They began in earnest at the Solvay conferences of 1927 and 1930, gatherings of the world's greatest physicists in Brussels convened to grapple with the new quantum theory. Einstein would arrive with a new thought experiment, a new way of arguing that quantum mechanics violated one principle or another. Bohr would spend the night working through it, and by morning he would have found the flaw. The exchanges were respectful, even warm, between two men who admired each other enormously. But they were also relentless, each man absolutely certain the other was wrong about something fundamental. Einstein never accepted the Copenhagen interpretation. He never accepted that the wave function was a complete description of reality. He never accepted that quantum mechanics, as formulated, was the final word on the nature of the universe. He believed, until his death in 1955, that beneath the probabilistic surface of quantum mechanics lay a deeper, deterministic reality, that God did not, as he famously said, play dice. He was wrong about the hidden variables as Bell's theorem demonstrated, but his discomfort, his instinct that something was missing, that the theory was incomplete, has turned out to be, in a different way, profoundly right. Not because there are hidden variables, but because the measurement problem is real, and the Copenhagen interpretation's refusal to engage with it is not a solution, but an evasion. Into this landscape, in 1957, stepped a 27-year-old graduate student at Princeton named Hugh Everett III, with an idea so radical that his thesis advisor, John Wheeler, the same Wheeler who would later devise the delayed choice experiment, worried it would be dismissed as crazy. Everett's idea was simple to state and staggering in its implications. He proposed that there was no wave function collapse, ever. The Schrödinger equation was always correct. Superpositions never resolved into single outcomes. What appeared to be collapse was not collapse at all, but branching. When you measure a quantum system in superposition, the measuring device, the scientist, the laboratory, the world, become entangled with the system. You too enter superposition. In one branch of the wave function, you have measured the particle here and it is spinning up. In another branch, equally real, equally physical, you have measured the particle there and it is spinning down. Both outcomes occur. Neither branch collapses. The universe splits, and both versions of you go on living in their respective branches, each convinced they have made a single, definite measurement. This is the many worlds interpretation of quantum mechanics, and it is, depending on who you ask, either the most daring and beautiful idea in modern physics, or the most extravagant and unprovable speculation in the history of science. Everett left physics shortly after completing his thesis. His interpretation was largely ignored for decades, dismissed by the Copenhagen consensus as metaphysical excess. Wheeler himself distanced himself from it, worried about the scandal it would cause. Everett went to work for the Pentagon, where he applied mathematical optimization to nuclear strategy, and he died in 1982, relatively young and largely unrecognized. Today, the many-worlds interpretation is considered by many physicists to be the most serious alternative to Copenhagen. It is favored, by informal surveys, by a substantial minority of physicists. Some surveys suggest as many as a third. David Deutsch, the Oxford physicist who founded the field of quantum computing, is one of its most prominent advocates. Sean Carroll of Caltech has written a popular book defending it. Its logic is compelling. It takes the Schrödinger equation literally, adds nothing extra, makes no arbitrary rules about collapse, and derives the appearance of a single classical world from the pure quantum dynamics. It is, in its way, the most conservative quantum interpretation there is. But it comes with a price tag that many physicists find too steep. An infinite, or at least a vast and continuously growing number of parallel universes, each as real as this one, each populated by versions of everyone who has ever lived, branching at every quantum event, in every particle, in every atom in the cosmos. An ontological profligacy on a scale that makes the Big Bang look modest. Is it real? Is the universe really, at this moment, branching into countless copies of itself? The answer is, we don't know, and there is currently no experiment that could tell us. Every branch is causally isolated from every other by the very logic of the theory. We can never observe another branch. We can never reach across the split and shake hands with another version of ourselves. And that itself is a kind of darkness, isn't it? The theory could be true, and we would never be able to confirm it directly. We would live and die in our one branch, never knowing whether the cosmos beyond our observation is one or infinite. Not everyone accepted either Copenhagen or many worlds. Some physicists looked at the measurement problem and concluded that something else, something not yet in the theory, was needed. Something physical, something real, that actually caused quantum superpositions to collapse. One of the most compelling proposals came from a man who is also, simultaneously, one of the most influential mathematicians of the 20th century, Roger Penrose. Penrose, the Oxford mathematical physicist who shared a Nobel Prize in 2020 for his work on black holes, proposed in the late 1980s that the collapse of the wave function was caused by gravity. More precisely, he proposed that quantum superpositions are fundamentally unstable because of the incompatibility between quantum mechanics and general relativity. When two different possible states of a system involve different distributions of mass, and hence different curvatures of spacetime, the two branches of the superposition cannot coexist indefinitely, because they correspond to different spacetime geometries, and spacetime cannot be in superposition. Penrose proposed a specific timescale over which this gravitational collapse would occur, short for massive objects, long for microscopic ones, which would explain why we never see superpositions of large objects. Their gravitational self-energy is large, so their superpositions collapse almost instantly. While quantum effects persist for electrons and atoms, their gravitational self-energy is tiny, so their superpositions last long enough to be observed. This proposal, called Penrose's objective collapse theory, or sometimes simply the Orr model for objective reduction, makes specific, testable predictions. A series of experiments called the M-Macro experiments, planned for a future space mission, would test whether superpositions of nanoscale objects collapse faster than quantum mechanics predicts, in a way that scales with gravitational self-energy. If Penrose is right, the results would not only solve the measurement problem, but would tell us something profound about the relationship between quantum mechanics and gravity, the two great theories of physics that have, for a century, stubbornly refused to be reconciled. Then there was the decoherence program. If Everett asked, "What if there's no collapse?" and Penrose asked, "What physical process causes collapse?" The decoherence program asks a different question. Can we explain why collapse appears to occur without actually postulating that it does? Decoherence is a real physical process, not an interpretation. It is the mechanism by which quantum superpositions effectively vanish when a quantum system interacts with its environment. When a particle in superposition interacts with the many trillions of air molecules, photons, and other particles that make up its environment, its wave function becomes entangled with all of them. The superposition is not destroyed. It spreads into the environment, but the parts of the superposition that correspond to different outcomes become, for all practical purposes, unable to interfere with each other. They decohere, They stop talking to each other, and from the perspective of any practical measurement, they look like separate, definite outcomes. Wojciech Zurich at Los Alamos National Laboratory has been one of the central figures in developing the theory of decoherence and its implications. His work on what he calls in-selection, the selection by the environment of preferred, stable classical states from the quantum superposition, provides a mechanism for understanding why the classical world emerges from quantum underpinnings. Why position, for instance, is a stable classical observable while superpositions of positions are fragile. Why the classical world we experience has the structure it does, rather than some other structure. Decoherence is powerful and important, but it does not, strictly speaking, solve the measurement problem. It explains why different branches of a superposition don't interfere with each other. But it does not explain why one branch is the one we experience. The branches are all still there in the mathematics. Decoherence turns a quantum superposition into something that looks like a classical probability distribution, but a probability distribution still involves multiple possible outcomes. Only one occurs. Why? Decoherence is silent, unless, of course, you accept the many worlds interpretation, in which case decoherence explains everything beautifully, because you don't need to ask why only one outcome occurs. They all occur. Decoherence just explains why we can't see the others. We have been in the weeds of quantum interpretation for some time now, and it might seem as though these are philosophical debates with no real consequences. Interesting puzzles for academics to worry about while the rest of science gets on with the work of understanding the universe. That view could not be more wrong, because the interpretation of quantum mechanics is not separate from the great questions of physics. It is entangled with them, deeply, inescapably, in ways that are only now becoming clear. Consider the question of time. Classical physics treats time as a background, a fixed universal stage on which the drama of physics unfolds. Einstein's special relativity made time relative. Different observers in different states of motion experience time flowing at different rates, but this relative flow is still part of a fixed, four-dimensional space-time, a block universe in which past, present, and future are all equally real, all simultaneously existing in the four-dimensional manifold of space-time. The distinction between past and future in classical physics comes not from any fundamental asymmetry in the laws, but from the second law of thermodynamics, from entropy, from the arrow of increasing disorder. But in quantum mechanics, time has a deeply different character. The Schrödinger equation is time-symmetric. It runs equally well forward and backward, but wave function collapse, if it is real, is not time-symmetric. Collapse is irreversible. Once a superposition collapses, it does not spontaneously uncollapse. If collapse is a real physical process, it introduces a genuine arrow of time into quantum mechanics at the most fundamental level. Moreover, quantum mechanics and general relativity have profoundly different relationships with time. In quantum mechanics, time is not a quantum observable. It is a parameter, a fixed external variable that the theory uses but does not describe. There is no quantum state of time, no superposition of times. Time is simply there, in the background, and the Schrödinger equation tells you how things change with it. In general relativity, time is dynamic. Space-time curves in response to mass and energy. Clocks tick at different rates in different gravitational fields. Time is part of the physical structure of the universe, not a background parameter. Near a black hole, time effectively stops. At the Big Bang, time itself may have begun. Combine these two pictures and you get an immediate, catastrophic problem. In quantum gravity, whatever theory must eventually combine quantum mechanics with general relativity, time cannot be both a fixed external parameter and a dynamic physical variable simultaneously. Something has to give. Either quantum mechanics is wrong about time, or general relativity is wrong about time. Or both are approximations to some deeper framework in which time emerges from something more fundamental. Some theorists have taken this last possibility seriously and arrived at extraordinary conclusions. Carlo Rovelli, the Italian theoretical physicist and author of 7 Brief Lessons on Physics, has argued in his formulation of loop quantum gravity that time does not exist at the fundamental level, that the equations of quantum gravity, when written without the approximation of a background time, have no time in them at all. Time, in Rovelli's picture, is not a fundamental feature of the universe, but an emergent one, an approximation that arises when a quantum gravitational system is observed by a subsystem inside it. The way that temperature arises as an emergent property of many interacting particles, even though no individual particle has a temperature. This is not a fringe idea, it is a serious theoretical program with significant support in the physics community. And if it is right, if time is not fundamental but emergent, then the implications for our understanding of quantum mechanics, cosmology, consciousness, and the nature of reality are almost impossible to fully articulate. Now consider consciousness. This is dangerous territory that serious physicists enter with considerable caution, because the history of mixing quantum mechanics and consciousness is littered with mystical overreach and embarrassing pseudoscience. But there is a serious, rigorous thread in this discussion that deserves attention. The measurement problem, as we have described it, involves the role of observation in determining quantum outcomes. The Copenhagen interpretation places the dividing line between quantum and classical at the level of the measuring apparatus, but it never specifies what counts as a measuring apparatus. Over the decades, some physicists, including John von Neumann, the brilliant mathematician who axiomatized quantum mechanics, and later Eugene Wigner, a Nobel laureate, have suggested that the dividing line is ultimately consciousness itself. In Wigner's version, a quantum system interacting with a measuring device places both in superposition. The measuring device interacting with a scientist places all three in superposition, and the chain continues until it reaches the mind of a conscious observer, at which point, and only at that point, the superposition collapses. Consciousness, in this view, is not just an emergent property of matter, but a fundamental feature of the universe, irreducibly necessary to complete the physical description. Wigner himself later abandoned this view. Most physicists dismiss it as introducing an unmeasurable, ill-defined element into an otherwise precise theory, but it refuses to die entirely, because it is the only interpretation of Copenhagen that gives a sharp, unambiguous answer to the question, what counts as a measurement? Roger Penrose has approached the question of consciousness from a different angle, arguing in The Emperor's New Mind and Shadows of the Mind that human consciousness involves non-computable processes that cannot be simulated by any algorithm running on a classical computer. He further argues that these non-computable processes arise from quantum effects in the brain, specifically in structures called microtubules inside neurons, and that the gravitational collapse mechanism he proposed for wave function collapse is the physical basis for these non-computable quantum processes. This proposal, made jointly with anesthesiologist Stuart Hameroff and called the orchestrated objective reduction, or ORCHES theory, is controversial to say the least. Most neuroscientists and physicists consider it unlikely. The brain is warm and wet, conditions thought hostile to the fragile quantum superpositions that Penrose and Hameroff need, and the evidence for non-computable processes in cognition is thin at best. But Penrose's broader philosophical point, that there is a deep connection between the unsolved problems of quantum mechanics, quantum gravity, and consciousness, that point is not easily dismissed. Three of the deepest mysteries in science: why quantum mechanics has the structure it does, how quantum gravity works, and why and how conscious experience arises from physical processes. All three are unsolved. All three may be connected, and the connection, if it exists, may go to the very heart of what the universe is made of. There is another implication of quantum mechanics so strange, so vertigo-inducing, that it warrants its own section, and it concerns information. In 1989, John Archibald Wheeler, the physicist we've already met, the man who coined black hole and devised the delayed choice experiment, delivered a lecture in which he proposed a radical new view of physics. He called it from bit. The idea was that physical reality, every particle, every field, every dimension of space-time, is fundamentally made not of matter, but of information, that at the deepest level the universe is a kind of computation, and what we call physical existence is the output of that computation. This was not a casual metaphor. Wheeler was the most rigorous of physicists, a man who had helped develop nuclear physics and general relativity, who had worked beside Bohr and Einstein. He was proposing as a serious physical hypothesis that information was the fundamental substrate of reality, that physical stuff, arose from bit binary choices, yes or no answers to yes or no questions. Wheeler's idea has grown, in the decades since, into one of the most active and controversial research programs in theoretical physics. The idea that the universe might be a computational process, that reality might be made of information rather than matter or energy, has been called the digital physics hypothesis, and it connects naturally with quantum mechanics because quantum mechanics is in many ways a theory about information. The wave function encodes information about the quantum state. Measurement is the act of extracting information. Entanglement is a form of information correlation. Decoherence is a process by which information about a quantum system leaks into the environment. In 2015, this informational view of quantum mechanics received what may be its most extraordinary theoretical support from a completely unexpected direction. A theoretical physicist at Princeton named Juan Maldacena had, in 1997, proposed a duality between certain theories of quantum gravity and certain quantum field theories without gravity, a profound equivalence between the physics of a volume of space and the physics on its boundary. Like a hologram, this duality, called the ADS-SAR-CFT correspondence, had in the intervening years become the most cited paper in the history of physics. In 2015, Maldacena and Mark van Ramstonk worked out a stunning implication of this duality. Two regions of space-time connected by a wormhole are, in the quantum gravity dual picture, quantum entanglement. The wormhole is entanglement, the geometry of space-time, the connections between regions, the distance between points, the structure of space itself, is a consequence of the quantum entanglement of the degrees of freedom that live on the boundary. Space-time itself emerges from entanglement. Space is woven from quantum information. This is the ER-EPR conjecture, named after two famous papers by Einstein from 1935, one about wormholes, Einstein-Rosen bridges, or ER, and one about entanglement, Einstein-Podolsky-Rosen, or ER. Maldacena and Susskind proposed that these two things, wormholes and entanglement, are the same thing, viewed from different perspectives. If this is right, and it is currently the leading theoretical framework in quantum gravity research, then the fabric of space itself is made of quantum entanglement. The universe is not a place that contains quantum particles. The universe is quantum entanglement, and space is what it looks like from the inside. And that means everything we thought we knew about what place means, about distance, about locality, about the spatial structure of reality, may need to be rebuilt from the ground up. By now, you have seen the core mystery. You have felt the weight of it, and you may be wondering, is there no escape? Is there no theory, no interpretation, no framework that resolves the measurement problem without either making the universe infinitely many, or making reality observer-dependent, or dismissing the question as unanswerable? There are attempts, several of them, and each one is, in its way, a fascinating and deeply instructive failure, not because none of them might eventually succeed, but because each failure teaches us something about how deep the problem goes. Let us walk through the main contenders. The first is Bohmian mechanics, also called pilot wave theory, developed in its modern form by David Bohm in 1952, though anticipated by de Broglie in the 1920s. Bohm's theory is, in certain respects, everything that Einstein wanted quantum mechanics to be. It is deterministic, given the complete initial state of the universe. Every future event is fixed. It is realistic. Particles have definite positions at all times. There is no measurement problem, because measurement is simply a physical interaction between a particle with a definite position and a measuring device with definite components, and the outcome is determined by the initial conditions. The wave function is real. It is a real field and configuration space that guides the particle through a precise trajectory, but it does not represent all of physical reality by itself. Particles exist independently, with definite positions, guided by the wave function. The price? The wave function of the universe lives in configuration space, not in three-dimensional physical space, but in a space with 3 dimensions for every particle in the universe. That is a space of astronomical dimensionality. This wave function is a real physical field according to Bohm's theory. It is non-local. It responds to changes in distant particle positions instantaneously, and the non-locality, while carefully calibrated not to allow faster-than-light signaling, is inescapably, explicitly non-local in a way that makes many physicists uncomfortable. Bohmian mechanics reproduces all the predictions of standard quantum mechanics. It cannot currently be distinguished from other interpretations by any experiment. Many physicists consider it the most satisfying realist interpretation available, and yet it has never gained wide acceptance, in part because of the extravagant nature of the configuration space wave function, and in part because extending it to relativistic quantum field theory, to the standard model to all the particles and fields we actually observe, has proven extraordinarily difficult. The second alternative is the family of spontaneous collapse theories. These are modifications of quantum mechanics, not interpretations but genuine modifications, making different predictions, in which the Schrödinger equation has extra terms added to it that cause wave function collapse to occur spontaneously, without measurement in a stochastic way. The most developed of these is the GRW theory, named after its creators Giancarlo Ghirardi, Alberto Rimini, and Talio Weber. In GRW theory, every particle has a tiny probability, per unit time, of spontaneously localizing, of having its wave function collapse to a narrow region of space. The probability is so small for individual particles that quantum effects persist for arbitrarily long times in isolated systems. But for macroscopic objects composed of many particles, the cumulative effect is that superpositions collapse almost instantly, in timescales far shorter than any practical measurement could detect. The GRW theory solves the measurement problem elegantly. It tells you exactly why Schrödinger's cat is always found either alive or dead, never in superposition. It is because macroscopic superpositions collapse spontaneously before any measurement is made. The collapse is built into the physics, but GRW makes predictions that differ slightly from standard quantum mechanics. Specifically, it predicts a small amount of noise in the positions of individual particles, a tiny random jitter caused by the spontaneous localization events. This jitter is being searched for in increasingly sensitive experiments involving ultra-cold atoms, nanomechanical oscillators, and other systems. So far, no such noise has been detected. The parameters of GRW have been constrained but not ruled out. The experiments continue. The third major alternative is the relational interpretation, developed by Carlo Rovelli in 1996. This is in some ways the most philosophically radical of all the alternatives, because it does not merely modify quantum mechanics or add to it, but fundamentally reconceptualizes what the theory is about. In the relational interpretation, the wave function is not a description of the quantum system by itself, it is a description of the quantum system relative to a particular observer. There is no universal wave function, there is no observer-independent reality. Every quantum state is a relational fact, a fact about the relationship between a system and an observer, and there is no fact of the matter about the state of a system in the absence of an observer. Different observers can have different, mutually inconsistent descriptions of the same quantum system, and both are equally correct relative to their respective reference frames. The collapse of the wave function is simply the update of one observer's description when they gain information about the system. There is no physical process of collapse. There is just information. This interpretation is deeply consonant with the spirit of relativity, the idea that physical descriptions are always relative to a frame of reference, and Rovelli has argued that it is the natural extension of Einstein's relativity to quantum mechanics. It avoids all the problems of many worlds, no need for a proliferating infinity of worlds, and all the problems of hidden variables, no non-local pilot wave needed. But it comes with its own philosophical price. In the relational interpretation, there is no objective reality. There is no fact of the matter about what the universe is like, full stop. There are only relational facts. Facts about what systems are like relative to other systems. This is a form of metaphysical anti-realism so thoroughgoing that many physicists and philosophers find it literally incoherent. The universe can't be made entirely of relations unless the relations are between something. Rovelli would say, that's fine. The universe is relations all the way down. There is no substance beneath the relations. Reality is not a thing. It is a web of interactions, and what we call things are just stable, persistent patterns in that web. This is either a profound insight or an evasion, possibly both. And then there is perhaps the most modern, most technically sophisticated set of alternatives, the various approaches to quantum gravity. These approaches, string theory, loop quantum gravity, causal set theory, and others, do not merely interpret quantum mechanics but attempt to extend it to a regime where it breaks down the Planck scale, where gravitational effects become as strong as quantum effects, and where space-time itself becomes a quantum object. At the Planck scale, a length of about 10 to the minus 35 meters, a time of about 10 to the minus 43 seconds. All the approximations that allow us to treat quantum mechanics and general relativity separately break down. This is the domain of quantum gravity, and it is here that physicists believe the next great revolution in physics will occur. String theory, the most developed and technically sophisticated approach, proposes that the fundamental objects of nature are not point particles, but one-dimensional strings of energy. Different vibrational modes of these strings correspond to different particles. String theory automatically incorporates gravity, automatically produces a quantum version of general relativity, and has a rich mathematical structure that many physicists find compelling. But it makes predictions, at least in its current formulations, only at energies so far beyond what any particle accelerator could reach that direct experimental testing is currently impossible. And it requires the existence of extraspatial dimensions curled up at the Planck scale that have never been observed. Luke quantum gravity, championed by Ravelli, Lee Smolin, and their colleagues, takes a different approach. It starts from general relativity and quantizes it directly, without introducing extra dimensions or strings. The result is a theory in which space-time itself is quantized, in which space is woven from a discrete network of loops, and the minimum volume of space is on the order of the Planck volume. Time may or may not emerge from this structure, depending on which version of the theory you use. Neither string theory nor loop quantum gravity has yet produced experimentally confirmed predictions that go beyond existing physics. Both are works in progress. Both contain beautiful mathematics and profound ideas, and both may be wrong. The honest answer is that we do not yet have a theory of quantum gravity. We have candidates and we have ideas, and we have increasingly sophisticated mathematical frameworks. But the theory itself, the one that will reconcile quantum mechanics and general relativity, that will tell us what happens inside a black hole, what the Big Bang really was, why the universe has the quantum structure it does. That theory has not yet been written. Let us zoom out now. Let us step back from the details, from the Bell tests and the wave functions and the spontaneous localization events, and try to see the whole picture. Let us ask what this century-long crisis in physics might mean, not just for science but for the human understanding of existence itself. A crisis of quantum mechanics is, at its core, a crisis about the nature of reality, about what the universe is made of, how it works, and, most troublingly, what role, if any, minds play in it. For most of human history, the implicit assumption underlying all science, underlying all rational thought, in fact, was that the universe exists independently of those who observe it. The stars were there before anyone looked at them. The dinosaurs lived and died before any human mind came along to think about them. The laws of nature operate without an audience. Reality is what it is, whether or not anything perceives it. This assumption is so deep, so foundational, that most people would not even recognize it as an assumption. It would simply seem like the obvious truth about the world. Of course, things exist independently of observers. What kind of childish solipsism would it take to think otherwise? And yet quantum mechanics, in its most austere and faithful reading, seems to challenge this assumption in a way that decades of experiment and the best efforts of the finest minds have been unable to deflect. Not the fringe versions, not the mystical overreadings. The austere, mathematically precise, experimentally confirmed theory, it challenges it like this. The universe at the quantum level does not have a definite state until it is measured. Particles do not have definite positions or momenta until these quantities are measured. Cats, if isolated from the environment well enough, do not have definite states of alive or dead until their state is observed. The wave function, the complete description of a quantum system, encodes not a reality but a set of potentialities, and only the act of measurement selects from those potentialities an actual outcome. This does not mean that if no one observes the moon, it does not exist. The moon is a macroscopic object, constantly bombarded by photons and cosmic rays and gravitational fields, constantly interacting with its environment in ways that force its quantum state to decohere almost instantly into the appearance of classical definiteness. Decoherence gives us a classical world. The moon is safe. But at the quantum level, at the level of individual electrons, photons, atoms, the definiteness we assume is not there. The superposition is real, the interference is observable, the non-locality is experimentally confirmed. Something that we call measurement, or observation, is genuinely, physically different from what precedes it. And in this difference lies a mystery that has not been resolved, and here is the part that makes physicists lie awake at night. We do not know where the quantum world ends and the classical world begins. We think we know it has something to do with scale, with the number of particles, with the rate of decoherence, but the exact boundary has never been specified by any version of quantum mechanics. The Copenhagen interpretation places the cut somewhere between the quantum system and the measuring apparatus, but cannot say exactly where. Every other interpretation dissolves the cut in different ways. None of them gives you a formula that tells you, at exactly this scale, in exactly these conditions, quantum becomes classical. This is not a minor gap in the theory, it is a chasm. And the chasm may not be fillable without a theory of quantum gravity that tells us, at the most fundamental level, what space, time, and matter actually are. Some of the most profound implications of quantum mechanics touch on the nature of the universe itself, on cosmology, on why there is something rather than nothing, on what the universe even means as a physical object. Standard quantum mechanics requires an observer, or at least a measuring apparatus, external to the system being described. But if the system is the entire universe, there is nothing external, there is no outside. The universe cannot be observed from outside itself. This is the cosmological version of the measurement problem. If you want to apply quantum mechanics to the universe as a whole, to ask what the wave function of the universe is, to understand quantum cosmology, to make sense of the Big Bang as a quantum event, you need an interpretation of quantum mechanics that makes sense without an external observer. The many worlds interpretation is the one that most naturally extends to cosmology. In Everett's framework, the wave function of the universe evolves unitarily, without collapse, and everything that can happen does happen in some branch. There is no measurement problem, because there is no collapse, and no need for an external observer. The universe is its own observer, in every branch simultaneously. This is why many worlds is taken so seriously by cosmologists. Not necessarily because they find the proliferating universes ontologically appealing. Many don't, but because it is the only interpretation that allows quantum mechanics to be applied coherently to the entire universe. But if many worlds is right, then the universe is not a single history. It's an unimaginably vast collection of histories, all equally real, branching at every quantum event from the Big Bang onward. The history we experience, the history of this particular branch, with this particular Earth, this particular civilization, these particular physical constants, is one thread in an infinite tapestry, special only in the sense that we happen to be in it. And the Big Bang, in this picture, was not the beginning of one universe, but the beginning of all of them. Every possibility was present at the beginning, and they have been branching apart ever since. Each branch diverging from the others at every quantum event, in every particle, in every atom, in every galaxy. The universe is not one story. It is all stories told simultaneously, diverging endlessly from a common source. There is a related puzzle, one that quantum mechanics makes especially sharp, about why the universe has the physical constants it does. The fine structure constant, which determines the strength of electromagnetism. The ratio of the proton mass to the electron mass. The cosmological constant, which determines the rate at which the expansion of the universe accelerates. These numbers have specific values that appear to be extraordinarily finely tuned for the existence of complexity, chemistry, and life. Change the fine structure constant by a small amount, and atoms could not form. Change the cosmological constant by a large fraction of its value, and the universe would either recollapse almost immediately, or expand so fast that matter could never clump together to form galaxies. We live in a universe whose physical constants fall within an extraordinary narrow range that permits complexity. Why? One answer, the anthropic principle, says simply that we couldn't observe a universe with different constants because such a universe wouldn't produce observers. We are here to ask the question because we are in a universe that permits our existence. This is not a causal explanation, but a selection effect. The answer is more interesting in the context of the many worlds interpretation or of string theory's landscape. If there are many universes, either the branches of the Everett wave function or the different vacuum states of string theory, and each has different physical constants, then the anthropic argument becomes genuinely predictive. Of course, we find ourselves in a universe with life-permitting constants. We could not exist in any other. The apparent fine-tuning is not tuning at all, but selection. This is the multiverse argument, and it is either the most powerful insight in modern cosmology or the most breathtaking abdication of explanation in the history of science, depending on who you ask. It explains the fine-tuning by multiplying universes. It buys explanation at the price of unobservable ontology. It may be right. It may be wrong. We don't yet know how to test it. Now let us sit with the philosophical implications for a moment longer, because they are enormous. If quantum mechanics is telling us that the universe does not have a definite state until measured, and if the boundary between quantum and classical is genuinely blurred, and if consciousness plays some role, even a vague, disputed, contested role, in defining that boundary, then we are in a situation that philosophy of mind finds deeply interesting. For several centuries, the dominant picture of the relationship between mind and matter was straightforward. Matter is fundamental. Mind is emergent. Consciousness arises from the complex organization of physical matter, from neurons firing, from information processing, from the electrochemical dynamics of the brain. Mind is what matter does when it gets sufficiently organized. This view, called physicalism or materialism, has been the working assumption of most scientists and most analytic philosophers. But quantum mechanics introduces a wrinkle, because quantum mechanics, in its most literal reading, seems to require something that functions like observation to be complete. The wave function evolves until an observation occurs. The observation is not a mere updating of human knowledge. In quantum mechanics, something physically changes when an observation is made. Something called the wave function collapses. And this change is not derivable from the Schrödinger equation alone. If consciousness is the thing that constitutes genuine observation, if there is no collapse until a conscious mind becomes aware of an outcome, then consciousness is not merely something that emerges from matter. It is something that matter requires in order to have definite states at all. Consciousness is not the output of physics. It is the prerequisite of physics. The universe would be, in some sense, a vast, indefinite quantum superposition without definite facts about anything until a consciousness came along and collapsed it into definite being. This is panpsychism meets quantum mechanics. This is idealism, the philosophical view that reality is fundamentally mental, expressed in the language of physics. It is a view that most physicists reject with considerable vehemence. But it is a view that flows with some inevitability from the logic of the Copenhagen interpretation pushed to its extreme. And even if we reject Copenhagen, even if we accept many worlds, or Bohm, or GRW, the question does not fully disappear. It transforms. In many worlds, consciousness does not collapse the wave function because nothing collapses the wave function. But why do we experience only one branch? Why does each conscious observer find themselves in a single, definite history rather than smeared across all branches? The answer requires some account of what it means to be a branch-specific observer, and that account inevitably involves something like consciousness. Quantum mechanics has not solved the hard problem of consciousness, the question of why physical processes give rise to subjective experience. But it has done something perhaps more unsettling. It has suggested that any complete understanding of physical reality may need to take consciousness seriously as a fundamental ingredient, not just an emergent one. If you've made it this far into one of the deepest dives in modern science, you deserve to know we're now approaching the final revelation, the part that ties everything together, the part that, if it's right, changes not just physics but our entire picture of what existence means. Stay with us. We have traveled a long way, from Max Planck staring at a furnace in Berlin to Bell inequalities violated in Vienna, from a cat in a box to the fabric of space-time woven from entanglement, from a young patent clerk proposing that light comes in lumps to theorists proposing that the universe is a hologram. Now we arrive at the deepest question, the one that all of this has been building toward. What is quantum mechanics telling us about the nature of reality? Not in the technical sense, we have covered the technical sense, but in the deepest, most fundamental sense. What kind of universe are we living in? What is the stuff of existence? What is the relationship between the observer and the observed, between mind and matter, between information and being? Here is the most honest answer that the combined weight of a century of quantum physics can give us. Nobody knows. But there are signs, there are threads, and when you pull them together, when you step back and look at the whole tapestry of quantum mechanics, quantum gravity, information theory, and the measurement problem, something extraordinary begins to take shape. Let us start with a fact that is easy to state and hard to absorb. The wave function, the mathematical object that describes a quantum system, does not live in space. It lives in configuration space, a mathematical space with 3 dimensions for every particle in the system. For a system of 2 particles, the wave function lives in a 6-dimensional space. For a system of 1,000 particles, it lives in a 3,000-dimensional space. For the entire universe, with its roughly 10 to the 80 particles, the wave function lives in a space of astronomical dimensionality. This configuration space is not a physical space. You cannot point to it, you cannot navigate through it. It has no relationship to the 3-dimensional space in which you live and move. And yet the wave function of the universe, the complete quantum description of everything that exists, lives there. This means something extraordinary. The 3-dimensional space we inhabit, the space of left and right, up and down, near and far, the space in which galaxies cluster and planets orbit and you sit watching this video, is not the fundamental arena of physical reality. It is a derived, emergent structure that arises when the high-dimensional wave function of the universe is viewed in the right limit. 3-dimensional space is not the stage on which physics happens. It is a pattern in the wave function. Space is not fundamental. Space emerges, and if space emerges from the wave function, what about time? What about causality? The principle that causes precede effects, that information flows forward in time, that the present is determined by the past. We have already seen that quantum mechanics has a complicated relationship with time. The delayed choice experiment suggests that the present shapes the past. The equations of quantum gravity seem to have no time in them at all. Ravelli's relational quantum mechanics and his work on loop quantum gravity both suggest that time is not fundamental but emergent. If space and time both emerge from something more fundamental, from the quantum state of the universe, from the entanglement structure of some deeper description, then we are not living inside space-time. We are living in a projection of something larger, something higher dimensional, something that the human mind was not evolved to directly perceive. This is the holographic principle in its most audacious form. And it is not speculation, it is the leading theoretical framework in quantum gravity research. Supported by the ADS-SCFT correspondence, by the ER=EPR conjecture, by the work of Maldacena, Susskind, Van Raamstonk, and dozens of others at the frontier of theoretical physics. The universe we experience, 3-dimensional, local, classical, is a hologram, a projection. A shadow cast on the wall of a cave by something much larger, much stranger, much harder to see. Let us go one level deeper. If space and time are emergent, what do they emerge from? The ADS-CFT correspondence suggests the answer: from quantum entanglement. The geometry of space-time, the distances between points, the connections between regions, the curvature produced by mass, is encoded in the entanglement structure of the quantum degrees of freedom on the boundary. Entanglement is the thread from which space-time is woven. Delete the entanglement and space-time tears. Add entanglement and space-time knits together. The geometry of the universe is a map of its quantum correlations. This is the ER=EPR conjecture at its fullest. 2 entangled particles, separated by any distance, are connected by a microscopic wormhole, a thread of space-time that the entanglement creates. In the interior of a black hole, the singularity is not a place where space-time ends, but a region of maximal entanglement, where the threads of wormholes from all the particles the black hole has ever swallowed converge into something indescribably dense and connected. And the Big Bang, the moment of maximum compression, of minimum volume, of infinite density, was a moment of minimum entanglement. The universe has been not merely expanding but entangling ever since. And what we call the expansion of space is, at the quantum gravitational level, the growth of entanglement. The universe is not growing in space. Space is growing because the universe is entangling. Now we arrive at Wheeler's it from bit in its most modern form, dressed in the language of quantum information theory. If space and time emerge from entanglement, and entanglement is a property of quantum information, a correlation in the quantum states of systems, then the universe at its most fundamental level is information, not matter, not energy, not space, not time. Information, specifically quantum information, the state of the universe at the Planck scale, is a quantum error correcting code, a structure in which information is stored non-locally, protected against perturbations, accessible only through collective measurements. The holographic codes that theorists like Ahmed Almheri and Daniel Harlow have been developing in recent years show that the structure of space-time, including the experience of locality, the sense that things are here rather than there, is precisely the structure of a quantum error correcting code. What we call space-time is the code. What we call matter is the information stored in the code. What we call physical laws are the rules of the code, the error correction mechanisms that preserve quantum coherence against decoherence, that ensure the stability of the patterns we call particles, atoms, molecules, planets, stars. And what we call observation, what quantum mechanics has always, mysteriously, placed at the center of its framework, is the act of reading the code, the act of extracting classical information from a quantum system, the act of decoding the universe. If this is right, and I want to be clear that it is a theoretical program, not yet a complete theory, work in progress at the most speculative frontier of physics, then the measurement problem has an answer, not the clean, simple answer we might have hoped for, but an answer that reframes the question so deeply that the old confusion falls away. There is no mystery about why measurement is special. Measurement is special because it is the fundamental act of physical reality. The universe is not a collection of objects that exist and then get measured. The universe is a quantum information structure, and what we call existence, the having of definite classical, local properties, is what happens when parts of that structure interact in the specific way that counts as a measurement. Existence and observation are not separate things with a mysterious relationship. They're the same thing. The universe doesn't have definite properties that get revealed by measurement. The universe is the process of measurement all the way down. This brings us finally to the question that no one has been able to answer, but that the whole edifice of quantum physics seems to be pointing toward. If the universe is, at its most fundamental level, quantum information, if space and time and matter and energy are all derived, emergent, approximate, then what is the quantum information made of? Information requires a substrate. A book requires paper. A computer program requires hardware. A hologram requires a film to encode it on. If the universe is a quantum error correcting code, what is the code running on? In every information system we know of, information is physical. It is instantiated in matter, in energy, in the configuration of physical things. Landauer's principle, proposed by Rolf Landauer at IBM in 1961, and experimentally confirmed, states that erasing one bit of information necessarily dissipates a small amount of heat. Information is physical. It cannot exist without a physical substrate. But if the universe is information, and information requires a physical substrate, then the universe requires a physical substrate that contains it. Something beyond the universe. Something in which the cosmic code runs. This is either a road to a profound truth or an infinite regress. Either there is, at the bottom, something that is not information, something that simply is, without being made of anything else, or information and physics are not in a substrate relationship at all. Perhaps they are identical. Perhaps information does not require a physical substrate because information is not a property of physical things. Physical things are a property of information, it from bit, without remainder. This is the precipice, the edge of what physics can currently say. Beyond here, the mathematics runs out and only philosophy remains. Here is what we know with confidence. The universe, at its most fundamental level, is quantum mechanical. Quantum mechanics is the deepest, most precise, most successfully tested theory in the history of science. It is not going away. Whatever deeper theory eventually supersedes it, whatever theory of quantum gravity eventually reconciles quantum mechanics with general relativity, that theory will have to reduce to quantum mechanics in the appropriate limit. It will not overthrow quantum mechanics the way Einstein overthrew Newton. It will incorporate it, explain it, ground it in something deeper. And quantum mechanics, in its most faithful, least papered over reading, says the following. The universe does not consist of independent objects with definite properties. It consists of quantum states, entities that are fundamentally probabilistic, fundamentally non-local, fundamentally holistic. The properties we observe: position, momentum, spin, energy. are not intrinsic to the objects we observe them in, but arise in the interaction between those objects and the measuring systems they interact with. Reality, at the quantum level, is relational. There is no absolute, observer-independent description of any physical system. The universe is not the clockwork machine the classical physics imagined. It is not even a collection of waves and particles. It is a web of quantum correlations, non-local, non-classical, non-reducible to anything more intuitive, governed by laws that are precise and powerful, and deeply, profoundly mysterious. And beneath even that, beneath the wave functions and the Hamiltonians and the Bell inequalities and the decoherence rates, there may be something even more fundamental, something that physicists are only now beginning to glimpse, something that may require not just new physics but new mathematics, new concepts, new ways of thinking about what a law of nature is, what existence means, what reality is. 125 years have passed since Planck looked to the furnace and asked a question nobody had thought to ask. In those years, the quantum revolution has transformed civilization. It has given us the semiconductor and the laser, the MRI scanner and the atomic clock, the quantum computer and the quantum cryptography protocol. It has rewritten chemistry, biology, materials science, cosmology. Every technology that defines the modern world is built on a foundation of quantum mechanical truth, and yet, the men and women who built this edifice could never agree on what it meant. Bohr and Einstein debated it until Bohr's death. Heisenberg and Schrödinger clashed over it. Feynman laughed at anyone who claimed to understand it. Everett walked away from it in disappointment. Bell proved that everyone had been wrong in a fundamental way. Penrose and Hawking argued about it in terms of black holes and singularities. And today, in laboratories in Paris and Vienna and Beijing and Princeton and Cambridge, the experiments continue, pushing ever harder at the boundaries of the quantum world, looking for the cracks where a deeper truth might show through. Because here is the thing that makes quantum mechanics not just a scientific puzzle but an existential one. If the universe is ultimately made of quantum information and if observation is the fundamental act of physical reality, then the universe is not indifferent to mind. The universe is not a blind machine grinding through time regardless of whether anything watches. The universe is, in some precise and technical sense, constituted by the act of observation, not by human observation. The universe managed to be observed long before humans existed, by the particles and fields and cosmic structures that interact with each other in the way quantum mechanics calls measurement, but by observation as a fundamental ontological category, woven into the fabric of what it means for anything to be real. You are not an observer of a universe that exists independently of you. You are a part of the universe's self-observation. The neurons firing in your brain as you think about these words are quantum systems interacting with each other and with the larger environment, performing the act of measurement that quantum mechanics places at the center of all physical reality. Your consciousness, whatever it ultimately is the universe becoming aware of itself in this place, at this time, in this particular, improbable, beautiful configuration of matter and energy and quantum information. The strangeness of quantum mechanics is not a problem to be embarrassed about, not a failure of the theory to be hidden behind the computational success. It is a message written in the most precise language human beings have ever developed, the language of mathematics, saying something that human beings have perhaps never been ready to hear. The universe is not what you think it is. And what it actually is, that question is still, after a century of extraordinary science, heroically, beautifully, terrifyingly open. We began with the impossible. We should end with the unanswerable, not because physics has failed, but because the questions that remain are the most important questions ever formulated, and the fact that they remain is not a sign of weakness, but of how far we have come. A century ago, we did not know the questions. Now we know them precisely, rigorously, in mathematical language. The questions we cannot yet answer are sharper and deeper than anything the science of the 19th century could have conceived. So let us end with the questions, not as a list, but as a meditation. What is the wave function? Is it real, a thing that exists in the world, or is it a mathematical tool, a compressed description of our knowledge about a system? If it is real, where does it live? If it is merely knowledge, whose knowledge? The universe's own. What happens during measurement? Is there really collapse? And if so, What causes it? Is it gravity as Penrose suggests? Is it spontaneous as GRW proposes? Is it simply an appearance as decoherence arguments suggest? Or does everything that can happen actually happen, in branches that we can never reach? Are there other worlds? Are there countless versions of this moment happening in parallel branches of a branching multiverse, each as real as this one, each inhabited by versions of everyone you've ever loved? And if there are, does it matter? Would it change how you live, knowing that everything possible is happening? Is space-time real, or is it an emergent, approximate description of something more fundamental? A holographic projection of a deeper quantum reality? Is the sense of being somewhere, of being here, at this place, in this body, in this room, an illusion that the quantum error correcting code creates to protect the information stored in the correlations between distant degrees of freedom? Is the universe made of information? And if so, what is the information about? What is the code running on? Is there a substrate? Or does information exist without a substrate? Is the universe, as some theorists are beginning to speculate, not a physical thing at all, but a logical structure, existing in the same way that mathematical truths exist, without any particular physical instantiation, necessary and eternal? What is time? Is it real, fundamental, irreducible? Or does it emerge from the quantum state of a universe in which there is no preferred time, in which the past and future are equally encoded in the present wave function, and what we call the passage of time is simply the increase of entanglement, the spreading of correlations through the cosmic quantum state? What is consciousness? And does it have a role in quantum mechanics? Not the role that mystical quantum consciousness theories give it. Not the role of causing collapse or creating reality by sheer force of subjective experience, but some subtler, more precise role? Is there a quantum theory of consciousness? Is there a connection between the hard problem of consciousness and the measurement problem of quantum mechanics? Or are these genuinely separate questions with no deep connection, and the apparent resonance between them is a philosophical illusion? What is at the Planck scale? What does space-time look like when you probe it at distances smaller than 10 to the minus 35 meters? Is it a continuous manifold, as general relativity assumes? Is it a discrete network of loops, as loop quantum gravity proposes? Is it made of strings, as string theory argues? Or is it something no one has thought of yet? Something that will require not just new physics, but a new framework for what we mean by physical law. And finally, the deepest question, the one that sits beneath all the others like bedrock beneath bedrock. Why does anything exist? Why is there a universe rather than nothing? Why does the nothing, the absence of space, time, matter, energy, information, law, not persist? Why did the quantum state of the universe begin? What does it mean for a quantum state to begin, when time itself is part of the quantum state? Quantum mechanics has taught us that the universe is not obligated to make intuitive sense. It does not owe us an explanation in terms we can picture. It speaks in the language of complex numbers and Hilbert spaces and operators and probabilities, and it is under no obligation to translate itself into anything more comfortable. But it also tells us, in the same language, with the same precision, that reality is stranger, deeper, more connected, more beautiful, more mysterious than anything we imagined before we learn to ask the question correctly. We are quantum creatures in a quantum universe composed of particles that are also waves, of matter that is also information, of brains whose neurons fire in patterns that are, at the most fundamental level, quantum mechanical. We evolved to navigate a world of medium-sized objects moving at moderate speeds, and we were given tools, mathematics, experiment, the fearless willingness to follow logic wherever it leads. That turned out to be capable of reaching far beyond the world we evolved for, and what those tools have found, in a century of extraordinary effort, is that the universe is not a machine. It is not a clockwork. It is not an indifferent void. It is something we do not yet have words for. Something that the mathematics points toward without the language being able to follow. Something that the experiments confirm without the intuition being able to grasp. Max Planck asked why hot things glow the way they do. The answer 125 years later is that they glow because the universe is made of quantum information. Because space and time are holographic projections of entanglement. Because observation is a fundamental feature of physical reality. Because nothing is definite until it is observed. And because every act of observation, including this one, The act of reading these words and thinking about what they mean. Is the universe, in a precise and technical sense, becoming aware of itself? And if that is what a question about a glowing furnace eventually leads to, then perhaps there is no question too small to ask. Perhaps every thread, pulled patiently enough, reaches all the way to the foundation. And perhaps the foundation, when we finally reach it, will turn out to be not the solid bedrock we hoped for, but something that shimmers, something that flickers between states, something that becomes definite only in the act of being asked. If you've reached the end of this documentary and you find yourself staring at the ceiling, wondering what's real, welcome. You're in good company. Some of the greatest minds in human history are staring at the same ceiling. The quantum world is not a place we understand, but it is a place we can begin to see, and that perhaps is the most extraordinary thing of all. If questions like these keep you up at night, subscribe. There is no shortage of wonder left. The universe is full of locked doors, and somewhere in the equations there is always another key.